Hello everyone, it's Benny, and welcome back to the Advanced Redstone Computer Series, at long last. In this video, we're going to be talking about the instruction set that our computer is going to be using, which is called SRCIS, the Standard Redstone Computer Instruction Set. And yeah, now if you've been following the series up to this point, you might be thinking, hey Benny, didn't you, already do a video on SRCIS, the Standard Redstone Computer Instruction Set? And yeah, I did. The reason why you're seeing this video is for two reasons. One, SRCIS has been drastically updated since I did that video. The version of SRCIS I showed in that video was SRCIS2. The version of SRCIS I'm showing in this video is SRCIS16. Yeah, there's been some drastic changes to SRCIS since I made that video. And so I figured I might as well give you, the more modern version, the one that's quite a bit better than the one I showed you back then. The other reason is, for some reason in that video, I was over-energetic and ridiculous, and the reason for that is, I don't know. It's a mystery to me as well, viewers, so I figured I'd go ahead and show you a better video on a better instruction set. So first thing I actually want to say about this instruction set is, yeah, you're probably intimidated by the fact that there's this giant sign wall of death, and I can understand that. But SRCIS is something called a dynamic instruction set, and I'll talk more about that when it's actually appropriate, but just know this. Even though there's about 50 signs telling you everything there is to know about it, you only need like 2 or 3 of these signs to actually implement it or use it. So yeah, there's a lot of information you can say about it, but you don't need all that information if you actually just strictly want to go in and use it. So yeah, don't worry, it's really not nearly as big and terrifying as it seems. And with that, I'd like to go ahead and start showing you the instruction set and stop boring you to death by staring at this sign wall and rambling on about nothing. So, let's go ahead and get started. So, first thing I'm going to talk about is the bit layout. And essentially, if I was to take this big fancy SRCIS program, all written out in binary, and look at all the instructions and say, what does it mean? That's what the bit layout is. It tells you what all the individual binary bits in an instruction actually mean. And it can look kind of intimidating, but I promise, it's really not that bad. So, I'm going to start with this red section right here. This is probably what you think of when you think of an instruction. This tells the computer what you actually want it to do. Do I want the computer to add some things? Do I want to subtract some things? Do I want to have it send some stuff to RAM? What do I want it to do? That's what this red section is. And this is called either the function or the opcode, whichever you prefer. Now, this blue section is a little bit trickier, but it's really not that bad. Let's take an instruction like addition. I want to add some things. Now, one way I could add some numbers is I could take 2 numbers in the computer, add them together. Boom. That's one way of doing addition. Another way I could do addition is, for example, maybe I want to take some existing number in the computer and just add something to it. So let's say I have 5, maybe I want to increment it, maybe I want to make it 6, maybe I want to add 7 to whatever number is stored there. I don't know. So, the point is, there's more than one way that I could perform something like an addition operation. And that's what the mode is. It tells it which way I want to perform addition, which mode I want to. And that's all these bits are. It sounds complicated, but I'll perform a demonstration in a second, and you'll see it's really not that bad. So now we're down to the last 3 sections, and these are probably the easiest. I'll stick with the example of addition. If I'm doing addition, well, I need to actually add some numbers. So, this register A section, this section tells it where the first number is. Where do I find the first number I want to add? And this register B section tells it, where do I find the second number I want to add? And from there, it's pretty straightforward. It'll find those 2 numbers, add them, And then this section tells it, well, where do I want to save this number I've just gotten from addition? And yeah, so there's A, B, and output. And again, it can sound kind of weird and confusing, but it's really not that bad. So let's go ahead and just do a demonstration of this. So for example, let's do this addition operation I've been harping on this whole time. Now, I could add some numbers already in there, but I'm starting from a blank slate. I don't have any numbers in there, and even if there are, I don't know what they are. So I'm just going to take my output, I'm going to add 5 to that. So that requires a special mode for that, a special mode for just adding to something that's already there. It happens to be mode 1, the immediate mode. So I'm going to specify a register. This output register that you see all the lamps attached to is register 7, so I'm going to specify that. I'm going to take the data in register 7, which, as you can clearly see, is right now 0, and I'm going to add 7 to it. And this is one of the few catches to it. If I am doing an immediate instruction, since I don't have any other registers I'm going to do it with, and of course I'm going to be saving back to the same register I'm reading from, rather than specifying all that, the remaining 6 bits just become the number I want to add. So I want to add 5 to that. Boom, there you go. If I go ahead and clock it, tell it to do this instruction, boom. As you see, the 2 registers now have 5 in them. So let's try that again. Let's do something different. Let's say I want to do register 5. And let's say I want to add 3 to whatever. Well, first off, let's just add. Actually, I got a better idea. Let's take nothing, and save it to register 5. This way I know register 5 is 0. So I'm going to clock it. And then, let's try that again. Let's go to register 5. Let's just add 3 to it. So, and again, add is 0, so don't need to worry about that. And there. Now I don't see that because that's not an output, but yeah. So now let's perform a non-immediate addition. I want to say, let's add register 5 and the output register. So that should add 5 and 3 and save it to the output register. Let's see what happens. So I'm going to go ahead and clock it. And there you go. I get 8. So, yeah. As you see, when you actually use it, it's the type of thing, it's really not that bad when you're actually using it. It sounds confusing, but like you just saw, it's really not that bad in practice. In fact, it's pretty easy to program with this. You can make the computer do pretty much anything you want without thinking about it too hard, so it's kind of nice like that. And yeah, that's the bit layout. That's all there is to it. I probably went on way too long about this and probably confused you more than I probably helped you, but it's really not that bad. So yeah, there you go. That's the SRCIS bit layout. So now that we hopefully understand how SRCIS's bit layout works, I'm going to talk about what I meant earlier when I said SRCIS was a dynamic instruction set. You see, SRCIS has this thing called the limb system, which stands for levels, modes, and branches, but essentially what this is it's an indicator of how complex or advanced of a computer you're making. So for example, if I have a limb of only 1, then I'd be making a very simple computer. It only has addition and subtraction. And in fact, I would only need these instructions and maybe a little bit of these. So that's what I mean when I say, if you don't want to, you don't need this big, giant, ridiculous specification. SRCIS is designed around real existing Redstone computers and the trends people have when they like to make them. And, therefore, this whole system is laid out roughly based on that. People have roughly 3 different directions they like to go in, and therefore, that's what the level mode branching system is based on. And therefore, it makes it really easy to take just about any existing computer of any complexity, and with relatively little difficulty, make it powered by SRCIS. And, yeah. So, again, that's just part of the idea that SRCIS is a general-purpose instruction set for Redstone computers. And, yeah. So, I just wanted to go over that briefly. And it's really not that complicated either. You have all the modes that you sort of get as you get more complicated. So you start off with basic register operations, like pretty much the only thing I had in my original Redstone computer that I built in my Building a Minecraft Computer tutorial. Then if you get more advanced, you can add immediate instructions. You can have numbers stored in the instruction. Get a little more advanced than that, you can have floating point numbers. Get a little more advanced than that, you can have single instruction, multiple data instructions. And yeah, so in levels, you start off with basic, just addition, subtraction. Then level 2, you get logic. Level 3, you can access external memory. Level 4, you get multiplication and division. So, yeah. Branching, again, starts out pretty simple. Start out with just equal, greater than, less than. Get more complicated, arbitrary conditions, unsigned versus signed logic. Get a little more complicated than that. You can load individual Boolean values to do a bunch of Boolean calculations. Get a little more advanced than that. You can do sort of branching-esque instructions with more than just your computer. You can send interrupts. You can have interrupt masking. You can have some control over the floating point unit and the summed unit that your computer has. And that's roughly how the lim system works. Couldn't think of it for a second there. Yeah, it's really not that hard to use. So it's pretty much just like a grid. So mode 1, level 1 would have add sub, add C, sub C, these instructions, then these branching instructions. And yeah, you get the idea, hopefully. It's really not that bad. You have some level, some mode, and some branch. People. Anyways, one moment. And with that, you pretty much understand all there is to SRCIS. It has a few wonky ideas that go into it, but after you get your head around those, it really isn't that bad. So, with that, I'm going to very briefly go over all the different functions that SRCIS can perform. And, like I said, it's going to be very brief. I'm not going to go in depth on it because that's going to take a lot of time. And besides, when I actually implement the instruction, I'm going to go more in depth on how it works anyways, so why bother doing the same thing twice, you know? So, I'm just going to go through them briefly so you know what they are. If you don't fully understand it, don't worry too much about it. So, to start off with, we have add. And surprise, surprise, this instruction adds two numbers together. Pretty straightforward. Subtract, just as straightforward, subtracts two numbers. Add with carry and subtract with carry are mostly the same as add and subtract, but with one difference. The difference being that they will use the carryout of whatever the last addition or subtraction operation was. They will use that operation's carryout as the carry in for that operation. And that's useful for doing things like more bit additions than your computer has. Like if you have an 8-bit computer, you could use these to easily do a 16-bit addition. And yeah. So, next up we have logic, OR, XOR, NOR, and. If you know logic gates, which you really should if you're watching the series, then you pretty much already know what they do. They just do that logic gate between all the different bits. So, OR will do OR between bit 1A and bit 1B, and then OR between bit 2A and bit 2B, or between bit 3A and bit 3B, etc., etc. And those are how the logic gates work. OR, XOR, NOR, and AND. They're the most common, OR, XOR, and plus NOR, just so it has a universal logic gate, so you can do any logical operation if you want. So, next up, SPC and LPC. They stand for Save Program Counter and Load Program Counter. And these are all about accessing the program counter, of course, which is, it's like this register, which always stores the number of whatever instruction you're on. So, for example, if I'm currently executing instruction 8, the program counter will be 8. If I'm executing instruction 175, the program counter will be 175. So these just let me access this, so I can save some number to it, so I can override it and jump to some other instruction. I can load it, so I can find out what instruction I'm on and add something to it, which is really useful for branching, by the way. And yeah, that's what those are. Save and load, those are used for accessing RAM. So I can save in some location in RAM. I can save some number there. I can load some number from some location in RAM. And yeah, again, fairly straightforward. Shift left, shift right, do exactly what you expect. They take all the bits and shift them either left or right respectively. Multiplication and division, again, exactly what you expect. They multiply and divide. Although it is worth mentioning, these instructions do have overflow. For example, if I multiply 15 times 15, which is the highest 4-bit number, I get 225, which is an 8-bit number. So I get some extra data there. And the way these handle the extra data is they store it in this register called the immediate register, or IR. And I'll go more on that later. And division, of course, that would be the remainder that's the extra. So, that concludes all the basic level instructions. These are all the traditional type instructions, which do some operation with registers or memory. And yeah, so now on to branching. First instruction, end. This is the most complicated instruction in the entire computer. What it does? It ends. It turns the computer off, shuts down, ends the program, does whatever. So yeah, it's a software shutdown, essentially. It can also exit out of an interrupt if your computer's in one, but more on that later. And yeah, branch equal, branch greater than, branch less than, does exactly what you expect. It takes two registers, either equal, greater than, or less than, respectively. And if they are, it branches. And branching in this system is it takes whatever's in register 7 and saves that to the program counter. So that's how branching works here. Branch 2, branch condition, BCD. That works by seeing if the bit is odd. So I could do a bunch of stuff with logic gates and do some Boolean operations and such, and then I can just test that with branch condition. If the last bit is 0, it doesn't branch. If it's 1, it branches. Pretty simple. Branch not equal to? Also pretty straightforward. If they aren't equal, then it branches. Branch unsigned greater and branch unsigned less than do the exact same thing as branch greater than and less than, except they do it with unsigned comparison rather than signed comparison. So, there you go. Now branch 3. There's SSR, which is set status register. Status register has things like carry flags, overflow flags, basically a whole bunch of information about the computer's current state. I can take that and I can save that to some register, and I can do stuff based on the status register if I want to. Set equal, that will save whether or not it's equal. It'll save 0 if they are, it'll save 0 if they aren't equal, it'll save 1 if they are. Save greater than, save less than, same thing. It'll save 1 if they're greater or less than, respectively, and 0 if they aren't. And yeah. Finally, last 4 instructions. SIR. SIR is send interrupt request. That allows you to send an interrupt request to, say, a GPU. You can tell it to, hey, stop what you're doing. You absolutely need to do this right now, or whatever. And yeah. And if your computer receives an interrupt, that's, again, what the end command is for. So you can use the end command to say, hey, okay, interrupt's over now. You can go back to what you were doing in the first place. More on interrupts when we actually deal with it. Set interrupt priority, which essentially says, for example, let's say, here's one of my favorite examples of this. Let's say we're having our computer fly an airplane for some reason. A high priority interrupt would be something like, hey, we need to give the pilot access to controls. So yeah, that's a high priority. A low priority would be something like, hey, we need to turn the lights on. So set interrupt priority lets you say, okay, if it's less than a certain priority, just ignore it. It's not important enough. And yeah. SFU stands for Send to Floating Point Unit. Essentially, what this is for is sending data between the floating point part of the computer and the non-floating point part, if you happen to have a floating point part, of course. And the way this works is it takes two registers and combines them together to make a single floating point number. In the way that one serves as the upper bits and one serves as lower bits. And at least that's if you're using it here. If you're using it in the floating point unit, then it will take the floating point number, convert it to an integer, and save it to your main integer processing computer part. And yeah, so it's for sending numbers between the floating point unit and the non-floating point unit. Finally, SMD does not stand for what you're thinking of. It stands for SIMD. This allows you to say whether or not the floating point unit acts as a SIMD unit instead. So SIMD and floating point are done with the same unit in this particular instruction set. And so if the number ends in a 1, then hey, we're going to activate SIMD mode and we're going to do SIMD stuff. If it ends in 0, okay, we're going to deactivate SIMD mode, just go back to floating point stuff. That's what that's for. And yeah, good God, that took 9 minutes? Well, whatever, those are all 32 instructions in it. Sorry it took so long, but there you go. And really with that, there's basically nothing else I have left to say except for like modes and some register stuff. So I guess I'll just go ahead and do that. So modes really aren't that different. In the RR register mode, which is the default 00, that does the type of thing you probably expect. It takes 2 numbers in the computer and does whatever the operation is with them. IR, immediate register mode, that does sort of the same thing, except it's doing with an immediate value rather than some other number in the computer. So you take some number and then do whatever operation with an immediate value rather than some second register. And yeah, FR and SIMD, like I said, they're technically the same. These are technically the same mode. This is technically both in mode 1.1, and which one it does depends on whether SIMD mode is on. So FR, floating point register mode, does the same thing as like RR. It does operations between 2 numbers in the computer, except it does it with floating point rather than integers. And SIMD, that does it with single instruction, multiple data, which is something I'll talk more about later. Essentially, it does it with 4 pieces of data at the same time. That's my best approximation for it without going in depth on what SIMD is. And yeah, that's basically all the different modes and such. Registers, pretty much what you expect. You have 0 through 7, and floating point unit has its own 7 registers. 0 on both of them is the 0 register, and register 7 is the branching register. So if I'm doing branching, it will jump to whatever address is there. And yeah, oh, and I almost completely forgot. The immediate register, which I talked about earlier. Yeah, you might notice that I only used 3 of the 4 modes. I used 00 for register, 01 for immediate register, and 11 for FR and SIMD. The final mode, 10, that is used to send one giant 14-bit immediate. So everything that isn't the mode specification counts as an immediate value. And that immediate value is stored in the immediate register. And the way you use the immediate register is when you use an IR command, all you have to do is just specify the immediate value as 0. And instead of using 0, because doing 0 will do absolutely nothing, instead of doing 0, it's going to use whatever value's in the immediate register. And there you go. So yeah. And other than that, I really don't think there's much else I want to say. I guess SIMD, when you're doing SIMD, it uses n over 2, so if I have 8 bits, then the SIMD will be 4 bits per number. The floating point unit uses twice as many bits as your processor uses, so if I have an 8-bit processor, it is a 16-bit FPU. And, and the mode where you send a giant immediate is IV for immediate value mode. And, I'm trying to think. Yeah, that seems about. Yeah, it seems like just about everything I care to share. So, that's all I can possibly say about SRCIS. So yeah, hope you enjoyed, hope you learned, and hope you're ready for next time, because we will be using this instruction set in our compute. Oh my god, I cannot believe I forgot to show you this. like I think I mentioned earlier, SRCIS is designed around real Redstone computers and how people really use them and how they really work. And one sort of consequence of that is when you decode a SRCIS instruction, it is incredibly simple. Sure, it's an encoded instruction set, but barely. Want to know how to decode an SRCIS instruction set? Well, you need a 32-bit decoder for the function, and you need a multiplexer for the registers. That's it. I'm not kidding you. That's all it takes to decode a SRCIS instruction. As you see, I did it pistonless. It wasn't even mostly efficient. I wasn't trying to go for efficiency here. And I still made a small and efficient decoder for SRCIS. And in fact, this has more hardware than it needs. I actually went ahead and did the AOU decoding in here as well, just because, why not? I had so much room in here. It's so easy to decode SRCIS instructions. I love that about it. But anyways, I'm getting off topic. So yeah, hope you enjoyed, hope you learned, and I'll see you next time.